All right, as we previously talked about, we cruised through chapters 1 through 13. They kind of made sense. They were a review of chemistry. They had a particular order. And now we've been covering specific things from kinetics of reactions to equilibrium constants to thermodynamics to electrochemistry. Now we're going to talk about nuclear chemistry, and really we're just going to touch the surface on nuclear chemistry to expose you to a couple of key terms when we talk about nuclear chemistry. We're going to skip a bunch of slides, so please note that when I go through this, we are going to skip some slides. So, review here. We have an element, we have the symbol, the top number, we have the mass number, and the bottom number, we have the atomic number. The atomic number is the number of protons and electrons. So if you want to figure out the number of neutrons, remember, you're going to take the mass number minus the atomic number. What we are going to focus on is really protons and neutrons, however. So remember, the protons and neutrons make up the mass of the entire atom together. Now, remember, there are isotopes. Not all atoms have the same elemental mass due to the fact that they have a different number of isotopes. So carbon, there's carbon-12 and carbon-13. Both carbon-12 and carbon-13 have 6 electrons and 6 protons. The difference is carbon-12 has 6 neutrons, carbon-13 has 7 neutrons. So, if we look at other examples of isotopes, we can look at uranium. There's uranium-234, uranium-235, and uranium-238 due to the varying number of neutrons in uranium. It's not uncommon for some of these isotopes to be unstable, or what we call radioactive, and we refer to these as radionuclides. And what happens is radionuclides can decay into different nuclide. So for example, let's look at the different types of radioactive decay that can exist. Right? Our first is alpha decay, which is the loss of an alpha particle. So here's the example with helium. You're going to look at uranium-238. It's going to break down. It's going to be radioactive. It's going to decay into uranium-234 and a helium atom. If you go 234 plus 4, you get 238. 90 plus 2, you get 92. So you can see the conservation of mass is still existing in decay. So alpha decay is the loss of an alpha particle. Beta decay is the loss of a beta particle, and a beta particle is a piece of energy. So an alpha particle, if we go back here, an alpha particle was essentially a helium nucleus or another type of atom. A beta decay is going to be a particular type of energy, such as an electron. So we can see here iodine is iodine 131 is going to decay into xenon 131 plus an electron. Now remember, an electron has no notable atomic mass, but its charge is -1. So it has -1 protons. Positron emission. Now what we have is a positron emission is the same thing as beta decay, except that it's a positive charge that's being emitted. So we have the opposite charge to that of an electron. So we have carbon-11 here breaking down into boron-11, and then we have the extra charge here to account for the proton. So a positron emission is the opposite of beta decay. Then we can have gamma emission. And gamma emission is the loss of a gamma ray, which is high energy radiation that almost always accompanies the loss of any nuclear particle. So just kind of something to point about. We have alpha decay, beta decay, and gamma emission. We also have I missed one, excuse me. We have alpha decay, beta decay, positron emission, and gamma emission. Anytime we have an electron capture, or the addition of electron or proton to the nucleus, it's known as an electron capture, or what we call as K capture. And this is the result of a proton transforming into a neutron. Now, we are not going to talk about neutron-proton ratios. I wanted to really expose you to the different types. I wanted to expose you to the different types of radiation so that we can practice with them. We're going to focus a teeny bit on K capture, but neutron-proton ratios we are not going to focus on. So you can skip slides 11 through 13. Excuse me, 11 through 22, and go to page 23. Slide 23. What we're going to focus on slide 23 is particle accelerators. And this is how we can kind of study these different types of nuclear chemistry is through particle accelerators. You can see here, here's a live picture. I'm pretty sure this is the one in Switzerland, or at least in Europe. The Hadron Collider. I could be incorrect on that, but you can see here the circle. They are incredibly large tracks with radii that are miles long. And that's kind of how we can study this decay and how particles react when they collide together. So remember, if we're going to study kinetics of a radioactive decay, so this is kind of the last bit here for 21.1, if we're going to study the kinetics of radioactive decay, it's a first order process, so we are going to obey and the natural log of NT over NO is equal to negative KT. The half-life process, remember we talked about the half-life process of reactions. A lot of times the half-life process of radioactive decay is more important. So if you want to figure out the time that it takes for half a sample to decay, you're going to take 0.693, which is really the natural log of 0.5, and divide it by K, your kinetic rate. And K is your rate. That is equal to your half-life. Every isotope has a different half-life. So that radioactive dating for carbon dating goes off of carbon 14 or carbon 12, or different carbon samples have different half-lives. Uranium has different half-lives. Typically, the more unstable an element is, the shorter its half-life is. When we measure radioactivity, this is just for your knowledge more than anything, we're going to use a Geiger counter, which measures the radioactiveness in a sample that's present. And we will go ahead and do this problem together in class. So if you want to write down this problem, if you missed the notes, we'll go ahead and we'll do this problem in class together, as it's going to take some time to go through this together, and we'll save the time on video. So that's going to conclude section 21.1 on nuclear decay and nuclear chemistry.